So I'm starting here with a summary of what we learned about Vesper theory in the previous video. And these figures come from your textbook, but I think they're a little over-detailed. I'm afraid they're going to make you think you need to memorize something, and really it's pretty straightforward. Let me point out the highlights. What we have in this particular figure are the basic electron pair geometries, assuming that we only have bonding pairs. So what I see is, for two electron pair domains, we get a shape like this, which is called linear. And for three, it looks like this, which you could anticipate, right? How do you get three things as far apart as possible? And that's called Trigonal Planar. Now, I know you can figure out these shapes, at least for 2 and 3 electron pair domains, but it's handy to have an image like this in your brain to call on. We want to construct knowledge, but it helps to have that image in there. On to the next figures. They show what happens when we start to replace bonding pairs with lone pairs. So these are for the species where the molecular geometry is not necessarily the same as the electron pair geometry. Based on 2 electron pairs, we get linear. Based on 3 electron pairs, trigonal planar, if all the electron pairs are bonding pairs. And if we replace a bonding pair with a lone pair, we get bent. But I hope you're not memorizing those names. Again, I hope they're making sense to you because your drawing looks like that. That was for 2 and 3 electron pair domains. Now here's 4, 5, and 6. And we keep removing one corner and another corner. And you'll remember I showed you those molecular geometries with my model kit. What I think is going to be more useful for our time together is to do some more examples of drawing molecules with the correct molecular shapes. So what I see here is carbon dioxide. And remember, to know the shape, we have to know the Lewis structure. So I'm going to do that quite quickly here. So that's not the tedious part of this lecture. What I see here for the first time is a double bond. And what we're going to do with double bonds is treat them the same as single bonds. Instead of counting electron pairs, I'm going to count electron pair domains or regions where I see electrons. So how many electron pair domains do I see around the carbon? I see 1, 2. And how do we get 2 groups as far apart as possible? Well, just by fluke, we drew this the correct way the first time. Carbon dioxide is a linear molecule. In this case, because they're only bonding pairs and no lone pairs, the electron pair geometry and the molecular geometry are the same. I would say linear for both. All right, N2H2. And again, we have to start with the Lewis structure. I think the skeleton is usually the hardest part of that, but remember, hydrogen can only make one bond, and you know why. So when I put the skeleton there, I will only put the hydrogens on the ends. We get a total of 12 valence electrons we get to put there. 2, 4, 6, 8, 10, 12. We're left with an incomplete octet on this nitrogen, so we're going to use that adjacent lone pair to make a double bond. And here is the Lewis structure. Just a little review there for you. Faster than I would have gone for the first time. All right, that's the Lewis structure, but Lewis structures weren't meant to show the realistic shape. Now we've got more than one central atom this time. But that's okay, keep your cool. We're going to look one atom at a time. How many electron pair domains do I see around this nitrogen? Remember, I count the double bond the same as a single bond because those 2 bonds have to point in the same direction in space. So I see 1, 2, 3 electron pair domains for that nitrogen. Its geometry is going to be based on trigonal planar. So here's a triangle around the nitrogen, but remember, one of the electron pair domains is a lone pair, not a bonding pair. Now, for the other nitrogen, how many electron pair domains do I see? Again, 1, 2, 3. So its electron pair geometry is trigonal planar. I'm going to put the substituents around it at the corners of a triangle. Now, it doesn't matter for now, but I'll put the hydrogen there and the lone pair at that corner of the triangle, although you just as well could have done it another way. Now, there's no questions written on these examples. The instructions aren't there telling you what to do. My voice is. If I ever wanted you to name the molecular geometry, I would tell you I wanted you to name the molecular geometry. And what I'm telling you for this particular case, because there's more than one central atom, there's no good name for the molecule as a whole. What I might say is that it's bent around each nitrogen, or that the electron pair geometry was trigonal planar around each nitrogen. Also, if I wanted you to tell me the bond angle, the instructions would have to say, tell me the bond angle. There's no routine I'm trying to get you to do just when I show you a molecular formula. So if I asked you for the bond angle here, what would you do? Well, 3 electron pair domains based on a trigonal planar based on 120. But because I have a lone pair, that's going to take up a bit more room, and that's going to squish that angle down a little bit. So I'm just going to say less than 120. I don't want to overstep my data. I don't know exactly what it will be. I just know it'll be a little bit less than 120. Next example, phosphorus trichloride. So again, we need the Lewis structure first. And at your leisure, this is what you will find. Now, phosphorus could exceed the octet, but I always start with the assumption that it follows the octet rule unless evidence slaps me in the face to the contrary. And I came up with a perfectly lovely structure without exceeding the octet, so let's just go with that. All right, that's its Lewis structure, but what's its shape? How many electron pair domains around that central atom? Well, I got to count the bonding pairs and the lone pairs. So I see 4. The geometry is based on tetrahedron. The electron pair geometry is tetrahedral. But because one of the electron pairs is a lone pair, not a bonding pair, the molecular geometry will be different. I'm going to draw a tetrahedron with a corner missing. I'm going to replace one of the bonding pairs with a lone pair. In my earlier video, I drew the whole tetrahedron and erased a corner, and you're welcome to do that. But with practice, I can do it without drawing the 4th corner in explicitly. I just put in a lone pair. Once I draw that structure, it's easier to see what the molecular geometry is called. That looks like a pyramid with a triangular base. The molecular geometry is Trigonal Pyramidal. And if I asked you what the bond angle was, let's see. Well, this is based on 4 electron pairs. The electron pair geometry is tetrahedral, so it's based on the tetrahedral angle. That lone pair, though, squeezes the bonds down a little bit. I'll just say it's a little bit less than the tetrahedral angle. How are we doing? Next example. Now, the new twist in this one is that I see hydrogens more than once in the formula. And remember I told you the skeleton is the hardest part? There may be clues to help you. Hydrogens can only make one bond, and we know why. So it's quite common to write the hydrogens after the atom that they have that single bond to. In other words, what I see is a carbon with 3 hydrogens on it and an oxygen with 1 hydrogen on it. So that's an invaluable clue to the skeleton. As our molecules get bigger, we're going to need clues like that. So now I can finish off the Lewis structure. Pretty simple. I'm going to draw that molecule with the correct shape now. One atom at a time, focus in on the thing you're interested in. Let's look at the carbon first. How many electron pair domains around that carbon? I see 4. So it's based on a tetrahedron. Now, I'm not going to draw my tetrahedron in exactly the same way I did before. I think it might be more convenient to draw the carbon-oxygen bond straight across. But I can finish my tetrahedron from there. To draw any tetrahedron, I'm going to put in a second bond at 109 degrees to the first one and in the plane of the screen. I'll put it up there, but you could have put it down below at 109 degrees to the other bond. Makes no difference at all. Same thing flipped over. Once I have the 2 bonds in the plane at 109 degrees, I know that the dash and the wedge are going to bisect the obtuse angle. I come out over here, and the dash just peeks out from behind the wedge. So I can reorient my tetrahedron any way I like. Now, what's the shape around the oxygen? Again, I see 4 electron pair domains, 2 bonding pairs and 2 lone pairs. So the geometry is based on a tetrahedron with 2 corners missing. It's bent around that oxygen. If I wanted the bond angles here around the carbon, I would say it would be about 109. A perfect tetrahedron would be 109, but I don't know if a carbon-oxygen bond takes up exactly the same amount of room as a carbon-hydrogen bond. So again, I don't want to overspeak my data. The oxygen has also a tetrahedral electron pair geometry, but the 2 lone pairs are going to squeeze that bond down a little bit, so I'm going to say less than 109. Again, because there's more than one central atom, I can't name the geometry of the molecule as a whole. I would just say it's tetrahedral around the carbon, and the molecular geometry around the oxygen is bent. All right, a couple more examples. HCN. Now, first atom's usually the central atom, except you know hydrogen can't be. Hydrogen can make only 1 bond, so we'll stick it on the end. That's the hard part. At your leisure, you can finish the Lewis structure, and here's what you will get. HCN. All right, I've done enough examples for you. I want you to draw it with the correct shape, name the geometry, and label the bond angle. Pause the video. All right, around that central carbon, I see 2 electron pair domains. The triple bond counts as 1 domain because all those bonds point in the same direction. The way to get 2 electron pair domains as far apart as possible from each other is directly opposite each other. I accidentally drew it with the right geometry. It is linear, both for the electron pair geometry and the molecular geometry, because there are no lone pairs. And finally, linear from your geometry class looks like 180 degrees. All right, last example. Krypton Difluoride. And you might think it's weird that krypton, being a noble gas, makes any bonds at all. But when we react it with very reactive fluorine, this has been known. I will never give you a molecule to do this that does not really exist. At my leisure, when I draw the Lewis structure, I'm going to end up with extra electrons on that central krypton. So let's, again, you go ahead of me. I want you to draw it with the right shape, name the electron pair geometry and the molecular geometry because they'll be different this time, and label the bond angle. All right, what do I see around that krypton? I see 5 electron pair domains. So the electron pair geometry is trigonal bipyramidal. You will need to practice and study a little bit so that those basic geometries come readily to your mind. Now, if I had a trigonal bipyramid with 3 lone pairs, I would take the 3 bonds off that central plane and leave the one that was straight up and straight down in my video. But that's the same thing as this drawn on its side. This is linear geometry as a molecular geometry. Pretty good game, huh? So very simple VSEPR theory gives us very good predictions of molecular shape.